chat hear me? Wonderful, thanks. Okay, as always, remember to do the seating survey, Chem 112, Section 002, ILC 118, and your seat number. Upcoming due dates, we have content video quizzes due tomorrow. There's an error in one of them. There are details below the link for that particular video. I recognize that the initial explanation that I put under that video link was extremely confusing and not very helpful. I've revised it, so hopefully that will help you get through that quiz issue. Thursday, midterm exam 1 becomes available. Friday, homework 5 is due, and Sunday, midterm exam 1 is due. Info on the exam. There is a Piazza thread that is, I'm continually updating with information on it as it develops. I posted a separate post about the new information that I added this morning. The biggest pieces of information are, I've definitely decided it's going to be a Blackboard test. I'm designing it to be done in 1.5 hours, and you will have 3 hours to do it anytime during that 3-day window that it's available to you. I will not be using a lockdown browser or one of those proctoring services. It's just going to be a standard test on Blackboard. The structure of the exam is going to be focused on a handful of systems that are going to be the contexts within which you will be answering the questions and applying the knowledge and skills that you've been practicing and gaining in the class. I have 3 of those systems figured out now, and I think I can get all of the remaining questions I need to ask into a 4th system, so I'm hopeful that there will only be 4 of these systems. I am planning on Wednesday morning to give you a document over Blackboard that contains the background information on all of these systems, so that you can start to get yourself familiar with it before the actual exam opens. And if there are any questions about the background information that's in there, there are 2 class periods and 2 office hours between Wednesday morning and Thursday afternoon when the exam opens for you to ask me clarifying questions. You can always, of course, ask me clarifying questions once the exam opens too, but I'm trying to give you guys a head start on that. So the way to think about this is, you know how in group activity 1, the system was water with surfactant molecules in it, and small group activity 2, the system was homeopathic dilutions. And in both of those cases, in order to answer the questions as part of those activities, you were applying the knowledge and skills that were more generally discussed in the class. And so that's the kind of thing that's going to be going on in these systems. That's the general idea at this point. Do we have any logistical questions to try to clear up before we move on to content today? Okay, so the muddiest point list from yesterday was quite long, and because it was quite long, I I wasn't able to get to everything, and I spent the time yesterday on all of the questions that were on exam 1 kinds of material, and I put off the kinetics material until today. And it turns out that having done that, the only muddiest points that were listed on Piazza that were left for today are our kinetics questions. So this is stuff that's related to the homework for this week. So that's what we're going to be focusing on. So Of course, once we get through these, because I don't think this will take the full time of the class, I'm going to open it up to any kinds of questions, exam or not related. Okay, so the first one is asking about how do you relate the rate of formation of one product to the rate of consumption of a reactant. So, and it's saying to report your answer as a fraction. So let's take a look at how this idea works. So our reaction is 4 NH3 plus 5 O2 goes to 4 NO plus 6 H2O. Okay. And the two we are concerned about is we want the rate of formation of this if we are given the rate of formation of this. So let's start by talking about R, the rate. The rate that we have is going to be something related to a change in concentration with respect to time. And because we want the rate of the reaction to be a positive number when the reaction is going forwards, we want, let's look as an example at the H2O as a product, because the concentration of H2O should be increasing as this goes forward, and so the change in this with respect to time should be positive, which is what we want. The reactants are going to be decreasing, so if it's a reactant, we need to put a negative sign in front of it. Now, for each time the reaction occurs, we make 6 molecules of water. So if the rate of the reaction is how many times does the reaction occur as written, we need to take this change and divide it by 6. So taking this change and dividing by 6 tells us that tells us how many times the reaction happens as written. Okay. We do the same kind of thing for the reactants here. So I mentioned earlier that for a reactant we need to have a negative sign because the reactants are going away, so its slope is going to be negative. And we want the rate of reaction to be positive when the reaction's happening. It's going to be something to do with the change in concentration of the O2. And each time the reaction happens as written, 5 oxygen molecules are reacted away. So we have to divide the change in concentration of the O2 by 5 in order to get the rate of the reaction as written. Okay. So if we look at how the question is worded, what must we multiply the rate of consumption of O2 by? So this is the rate of consumption of O2 in order to get the rate of formation of this. Okay. So we have an equation here and we'll just solve it. So if we multiply through by 6, we get dH2O dt equals -6/5 dO2 dt. And so that is what you multiply the rate of consumption of O2 by to get the rate of formation of H2O. So that just comes straight from the stoichiometric coefficients. Are there any clarifying questions? Okay, from the chat I see a question. I'm using a D instead of a delta, right. So here's the idea of that. The textbook uses deltas, and I don't know which Newton uses. So if we plot the concentration of one of the reactants as a function of time, what we're looking at as the rate of change is the instantaneous slope. So it's going to be the tangent of these of the curve at this point, and so that is the notation for these this expression here, the derivatives. Okay, so this is a tiny, tiny bit of calculus, but we're not actually doing the calculus here. We're just understanding the notation of the calculus here. So, a lot of textbooks talk about the change as delta concentration of H2O. Well, okay, let's do O2 since I have this going down, over delta T. And that is the approximation of saying, okay, I'm going to take some time here, I'm going to take some time here, and I'm going to approximate it as the change in between. That's much less precise than using the derivatives, and I think it introduces some extra confusion to do it that way. So I don't tend to use the delta notation. Okay. So what we have here is d H2O dt is the derivative of the concentration of water with respect to time. Okay. All right. Any clarifying questions on this kind of concept of manipulating rates and their relative rates of different components? Okay. So the second question we've got, relating rates when expressed in concentration versus pressure. So there is, when we went through the explanation of the rates, now let me bring this back up over here. When we go through the explanation of the rates, these are expressed in terms of the concentration. And that makes perfect sense if what we're talking about is a reaction that is happening in solution. If we are, however, we're looking at, say, a gas phase reaction, then it is often more convenient to talk about the amounts of the reactants and the products that we have in terms of partial pressures instead of being in terms of concentrations. And fortunately, those two concepts are easily related to each other. So if we look at the ideal gas law, PV equals nRT, pressure, volume, number of moles, ideal gas constant, and temperature. We're going to use this in a second. What is concentration in molarity? How do we express molarity? Yes? Moles per volume in liters, correct. So molarity is moles of solute over liters of solution. Well, we've got moles, we have liters. So let's solve this for that. N over V equals P over RT. Okay. So N over V is just concentration in molarity. It may seem strange to think about the concentration of a gas, but the units are the same. It works. And so that means that pressure gives us a measure of this, and it's just there's a scaling factor of 1 over RT that's associated with it. Okay? So when we look at a reaction like this, and we express the rate in terms of the change in concentration, we could also write it, if we wanted to, as 1/6 derivative of the partial pressure of H2O, if this is a gas phase reaction, dt. If we are doing if we are measuring the amounts of materials via their partial pressures. And so if we call this our P, meaning that we're measuring it in terms of pressure, and if we call this our C because we're measuring it in terms of concentration, the relationship between the two is just this, 1 over RT. So RP over RT. Oh, this is unfortunate that we're using R for two different things. So this R with the subscript is meaning the rate. This R is meaning the ideal gas constant. I just now noticed that could be a confusion here. And then this is going to equal RC. Now, I am not going to be asking you to convert between the two. The point of this discussion is to understand the general concept that even though all of the kinetic stuff that we're developing and we are coming up with equations for, they are expressed in terms of concentrations because we're picking one of these two to do. And just the overall idea is if you take out the concentrations and put in the pressures, it works just the same. And so your rate constants would end up, or your rate coefficients would end up getting, being a different value because they're in different units. They're in pressure units instead of concentration units. But the idea of, but all of the math is identical, whether we do it in pressure or we do it in concentration. All right, any clarifying questions about any of that? Yes, temperature needs to be in Kelvin for the ideal gas law. Okay. All right. How do I determine the order of reactions? Okay, there are two different ways to interpret that question. One of them is if I am given a differential rate law, what is the order of the reaction from that? So if we have a rate law that equals a rate coefficient times concentration of a species to the second power, this is the order of the reaction. Specifically, it is the order of the reaction with respect to species A. But in this case, the overall order, well, in every case, the overall order is the sum of all of those exponents. And since there's only one here, it's the same thing. So this is a second order reaction. So that if you have the differential rate law, you just look at the exponents to see what the order is. If you have a, if you are looking at experimental data and are trying to figure out what the rate law is from the data without having the rate law yet, then you have a couple of different options for determining what the order of reaction is. One of them is the method of initial rates. So if you have data where you have the initial concentration of species A, initial concentration of species B, and then the initial rate, and then you run a bunch of experiments and say you have this is, say you do 1 molar here, 1 molar here, and you get a rate of 1. If you then do 1 molar here, 2 molar here, and you get a rate of 4, then doubling the concentration of B quadruples the initial rate, so that tells you that the order with respect to B is going to be 2, because 2 squared gives you 4. Okay. Then if you do something like 2, 2, so that you've doubled A in this case, and then this goes to a rate of 8, then doubling A doubled the rate, so that would be A to the first power. Okay, so that is one way to determine the order of reactions, is to conduct a series of experiments, measure the initial rates, and carefully choose your reaction conditions such that you're holding one species constant and are doing convenient changes in the concentration of the others. The third way you can do it, also from experimental data, is for a case where you think that there's only one concentration that's going to end up mattering, you can plot the concentration of that species versus time. If you end up with a straight line, then this is 0th order. If you plot the natural log of the concentration with respect to time, and you get a straight line, then it's 1st order. If you plot 1 over the concentration with respect to time and you get a straight line, then it is second order. So that approach works in those special cases where there is only a single reactant that is mattering in the case, and where the reaction order is either 0, 1, or 2. Now it turns out that you can, that many cases fall into this category. So this is actually much more common than it sounds. And even in cases where it isn't the case, where there are multiple things that reactants that matter, you can use the method of flooding in order to turn the situation into one where only one matters. And there are later questions about that. Okay. Any clarifying questions on how to determine the order of reactions? Anything from the chat?
If you want to demonstrate how to find order of reaction again, I think that would be really helpful.
Demonstrate how to find it again. Okay, so the three options are if you have the initial, if you have the differential rate law, you just look at the exponents. Experimentally, if you don't have the differential rate law, then you can either use the method of initial rates, or if you only have one thing that, one reactant that matters, you make these three different plots and see which one is a straight line. So that's the, those are really your options to work with. Okay. And yes, the first one says 0th order. Okay. All right. Next, integrated rate laws. How do we know which equation to use? Okay, so the integrated, basically it comes down to this. You use the equation that's determined by which order it is. So a 0th order reaction has the equation concentration of species A equals the initial concentration of species A minus KT. If it is a first order reaction, we have concentration of species A equals the initial concentration of species A, that's a 0, times E to the negative KT. And then for the second order reaction, the way I remember this one is 1 over concentration of A equals 1 over concentration of A naught minus KT plus KT, I think. Yes, plus KT. But you can then solve this if you need. A is going to be 1 over all of this stuff. So in order to know which of the integrated rate laws you use, you have to know which order it is. That's it. Any clarifying questions on that issue? How to know which equation to use? Okay. Method of flooding. What is it and how does it impact the concentration of different species or substances? Okay. So let's suppose we have some kind of reaction, A plus B plus C goes to products. And we expect that the rate of reaction is going to be of the form some rate constant K times A to some power times B to some power times C to some power. And we want to determine what all of the powers are and what the rate coefficient is. So the idea of this is to set our initial concentrations such that one of them is very small compared to the others. Oh, that should be a B. C. And so these are the initial concentrations. Okay. So if we think about this reaction happening, by the time the reaction is complete and all of the A0 has reacted away, we will have a final concentration of A of 0, final concentration of B of 0.999, final concentration of C of 0.999. Now, both of these are barely changed from where we started here. But the reaction can't go any further because you've run out of one of the key reactants. So what that means is that over the course of this entire reaction, these two values are effectively constant. They change so little that they're not going to be changing as the reaction progresses. And so what you can do is now fold them into a constant we're going to call K observed, which is going to be K times the concentration of B to the Bth times the concentration of C to the Cth, which will mean that our rate can now be rewritten as K observed times A to the A. And so the B's and the C's just fold into that constant, that rate coefficient here. This is called the method of flooding because we have flooded the system with B and C. It is alternately called the method of isolation because we have isolated the concentration of A as being the one we're looking at. Okay? So if we look at this expression right here, it only depends on one concentration, and we know what to do in those cases. We can plot them. Okay? So let's suppose that we do in fact plot this, and we plot the natural log of the concentration of A versus time, and let's suppose we get a straight line. We declare victory at that point because we know that A here is 1. We also know that the slope of this is negative K. In this case, negative K observed. So, here we go. So we now can say R equals K concentration of A. We know that that's to a 1, B to the B, C to the C. So we've started to clarify what the rate law is by finding out what that exponent was. Now that we have a value for K observed, notice that we can flood the system with different amounts. So suppose we then say, no, I'm going to have another experiment where concentration A is the same, concentration of C is the same, but now I'm going to have concentration of B be 2. It's still flooded. We can still make the same approximation, but we are going to now get a different K observed value because K observed depends on how much B there is. So what we can do then is do this for a whole series of different B's, and we will plot our K observed as a function of the initial concentration of B. And let's suppose that our K observeds do something like that, and they form a straight line. Well, look at our expression here for K observed. What's the exponent of concentration B have to be if this is a straight line? The chat says 1, and that's correct. So it's saying that K observed is linear in B. So we have a straight line. We now know that this is 1, and our growing rate expression, A, B, and then we don't yet know C. Now, but we can change what the concentration of C is. We can do K observed, keeping A and B the same values, and now we're changing the concentration of C that we have. And now, suppose we see something that looks like this. And we can fit that expression, and maybe we find that this is a quadratic. Quadratic means C would be 2. So we now know that our rate is K, concentration of A, concentration of B, concentration of C squared. And then at this point, we now have a bunch of different values of K observed. We now know that this is 1, this is 2. So we know which concentrations we used in each of those experiments. We know this value. The only unknown is K. And so you can find your rate coefficient from any of these points, or all of them and average them, something like that. So that is the method of flooding, and it's extremely powerful, an extremely powerful way to be able to take a complicated rate law and turn it into something that is manageable, turn it into something that's tractable. Are there any questions, clarifying questions on this? Yes?
So to find the K value, you said we could either use just one or average all the 3 of them. If we use just one, is it going to be the same as if we average all 3?
It's going to depend on the quality of your data. My general approach would probably be to do all of the determinations and then average them. But you know, if your data is pretty high quality, then you may not. It may not make much of a difference. Yeah.
Someone was just wondering how they got the final concentration from this. So this is going to be like data, correct?
So getting these from this?
Yes.
Okay.
They're confused on where those final.
Gotcha. Okay. So what happens here is we look at the reaction stoichiometry. For every molecule of A that reacts away, 1 molecule of B reacts away and 1 molecule of C reacts away. So if we have 0.001 of the A naught here, and all of that reacts away, then we subtract this from this amount to find out how much of B is left. So this is kind of like a limiting reagent problem back from Chem 111. So, but we're just doing it in terms of concentration instead of doing it in terms of the actual number of moles. This is moles per liter. So, all right. Any other clarifying questions on method of flooding? Yes?
Where are you seeing that C is 2? Are you just like...
Okay, good question. So here, the idea was, it's clearly not linear, right? It's going up as a curve. And so the question at that point would be, what is the shape of that curve? And so you would probably do some kind of numerical fit to the data, like a least squares fit to it to find out what it is. The easiest thing to do is if you see a curve like this that you suspect is second order, where you expect that this is squared, then you could take your K observed values and then plot them as the square root of the K observed versus concentration of C. And if it is squared, you would get a straight line there. So that would be one way you could do it without having to go through like a least squares fit. Does that make some sense? Okay. Yeah, it's kind of convenient that in most cases, reaction orders are integers. So if you see a curve on one of these kinds of plots, it is probably second order. It could be third order, but we're not really going to see third orders this early in chemistry. It could be 1.5 order, 3/2 or something like that, because fractions can occur sometimes, but not in general chemistry. Okay. All right. So that is method of flooding. So there was also a question about, at the end of the method of flooding video, I went back to an earlier example where we had water as part of the reaction. It was being produced, and it was in aqueous solution, so that water was also the solvent that you're dealing with. And I made the comment that I didn't include a rate for the, I didn't include a dH2O dt because the concentration of the water is not changing very much relative to its initial concentration. And that's exactly the same concept that we have here, where we've flooded the system with these solutes, and this solute is at a very low concentration, so the changes that we see here are minimal. Well, if you're dealing with solutes in a solvent, and the solvent is participating in the reaction, then almost by definition, you have already flooded the system with the solvent. Okay, and so the question was, is this always the case that you leave out the solvent, or is it just for water? It pretty much always, whichever solvent you're using, you will leave it out. Anytime you have a reaction where the solvent is participating in the reaction, its changes in concentration are going to be negligible. Another case can be something that's related to this. Imagine that we have some kind of reaction, A in solution phase, plus B, which is a solid that the solution is in contact with. Maybe you've got a crystal or something that is inside your solution, and there's a reaction that happens on the surface of the crystal, and then it forms some kind of products. Well, you're not going to, you can't really talk about a concentration of a solid very effectively, because it's, that concentration is going to be a constant. Because concentration is how many moles of substance you have divided by the volume that that substance is occupying, and that is a constant for your solvent, that's for your solid, that is just dependent on its density. So, so you will not find in these cases that you will not have a concentration of B that figures into a rate law. Incidentally, it is situations like this where you have a solid surface that is interacting with a solution or a gas that generally gives you zeroth order reactions. So of the three main types here, zeroth, first, and second order, zeroth order is the least common, and that's because it is a reaction type that is usually something that is happening at a surface. And we might get into why that is next week, but I'm not actually positive of that yet. So if you think about something like the catalytic converter in your automobile, which turns carbon monoxide into carbon dioxide. So it's a gas phase reaction that's happening on the surface of platinum or palladium particles that are in the catalytic converter. And so those kinds of reactions are very often zeroth order. And yes, the question from the chat, kinetics is going to be on midterm exam number 2, not midterm exam number 1. Okay. That is the list of muddiest points that I've been given on Piazza. So I am happy to open up the floor and the chat to any questions of any kind. What can I help with? Yes?
Yeah, I just had a quick question about the exam. Like,
Sure.
You said it was going to be based on systems and kind of where we group assignments. Are the questions on the exam going to be similar to the questions asked on the group assignments or the quizzes associated with group assignments?
So not quite in the same way, because the small group assignments are designed. So for the chat, the question was, since the small group assignments are organized around a system, and since the exam is also going to be organized around systems, will the types of questions be the same as on the exam as they were in the small group activities? And my answer to that is no, because the goal of the small group activities is to lead you through a discovery process from question to question using the Socratic method. And so I am asking you questions trying to elicit the construction of a new understanding of something. Whereas for the exam, the reason I'm using systems in this case is to provide sort of a unifying context about which I can ask a bunch of related questions that are getting at your understanding of the material. So the goal of that is, I don't want every one of the questions to have you need to understand a new system, but because the questions are going to be application questions. And if there are, I don't take this as how many questions are on the exam. I'm making this number up. But if I had 50 questions, I don't want you to have to learn 50 new systems. So the goal of the systems in the exam is to group them so that you spend some time understanding that one system, and then you have a set of questions that all relate to it, so you're not having to learn something new each time. Yes, so what do I mean by a system? And yes, it is similar to a scenario or a context. I'll go ahead and give you a preview of one of them. One of the systems is seawater, okay? And so the background information that I'm going to be giving you Wednesday morning is going to be things like, here are the concentrations of different ions that are present in seawater. And so then you can imagine the kinds of questions I could ask based upon having a complex mixture of a bunch of different ions, rather than having a single ionic compound that has dissolved into into your solution. Okay, so when I'm saying a system here, that's the kind of thing that I'm talking about. Okay. What else can I chat with you about or help clarify? Van Hoff factors, okay. So, Van Hoff factors relate to colligative properties. There are 4 colligative properties: vapor pressured lowering, boiling point elevation, freezing point depression, and osmotic pressure. All 4 of these depend only on the number of particles of solute that you have, not the nature of those solute particles. So the Van Hoff factor is an attempt to an attempt to get the correct number of particles that are generated when you dissolve something in a solvent. So let's look at how that works. Vapor pressure, each one of these has an equation associated with it. We have the vapor pressure lowering is the vapor pressure of the solvent is equal to the mole fraction of the solvent times the vapor pressure of the solvent when it is pure. Boiling point elevation, we have the change in the boiling point is equal to the concentration of the solution, of the solute in molality times the boiling point elevation constant for that solvent. Freezing point depression looks nearly identical, just with a freezing point depression constant instead of a boiling point elevation constant. And osmotic pressure is the ideal gas constant times temperature times the concentration of the solute in molarity. So the key here is that we have this quantity, this quantity, this quantity, and this quantity that are all related to how many particles of solute you have in the solution. The issue comes when we have something like, let's say, magnesium chloride that we dissolve into water. Like so. So for each formula unit of magnesium chloride, we get 1 plus 2, 3 particles that are dissolved into the liquid. Okay. So what this is what we call the Van Hoff factor, I, excuse me. And so in this case, our M that we're using needs to be the molality of the formula units times our Van Hoff factor. Same thing, and so that's true for both of these. And then here, our molarity needs to be the molarity of the formula units times I. The one that's a little bit annoying is the mole fraction, because mole fraction is the mole fraction of the solvent. So that is number of moles of the solvent over the number of moles of the solvent plus the number of moles of the solute, so we'll say formula unit, times I. Okay. Now, this value of 3 that I put here is an estimate. It is an estimate because in solution, these ions can occasionally pair up. So because opposite charges attract due to Coulomb's law, the magnesium and the chloride ions can occasionally come together and form an ion pair that in solution is acting as though it is a single particle rather than the 2 separate particles that you started with. So the I of 3 in this case is our predicted value that is going to be sort of an upper limit we could have to what I is experimentally. The actual I will be something less than 3 because some of these will pair up into ion pairs. How much less than 3? The only thing we can really say about that is comparatively. So the more concentrated the solution is, the closer together on average these ions will be, and so the more ion pairs you will end up having. So if your concentration is 0.01 molal, then you might have an I of 2.8. If it's 0.05 molal, you might have an I of 2.6, something like that. You also can then do comparisons of something like, if you're comparing magnesium oxide to sodium chloride, when these split up, sodium chloride becomes singly charged ions, magnesium oxide becomes doubly charged ions. The attraction between doubly charged is much greater than the attraction between singly charged, so you would expect the magnesium oxide to have a smaller Van 't Hoff factor than a similar concentration of sodium chloride. So those are the kinds of relative comparisons that you can make. They are, you will not have to come up with specific numbers for the Van 't Hoff factors. They are experimentally determined. Now, if you were given a colligative property, say, maybe you were given what an osmotic pressure was, and if you knew what concentration you had made, then you would be able to use that information to calculate the Van 't Hoff factor from that experimental data. But you're not supposed to just, you're not able to look at the chemical formula or the Lewis structure or something like that. You can't do that and come up with a number for the Van 't Hoff factor. Can I do an example? Okay, sure. An example of finding the Van 't Hoff factor from experimental data? Okay, we can do that. The problem is making up numbers off the top of my head, I may get a really crazy Van 't Hoff factor. I'll tell you what, I will go through the procedure without a specific number in it so that you can see how it works. So suppose you are given an osmotic pressure, pi. Okay. And you are given the mass of, let's say, sodium chloride that you dissolve in 100 mils of water. Okay. So you take your mass, so grams NaCl, some number. You then use the molar mass, sodium chloride, mole, sodium chloride. I'm going to assume that you can determine what the molar mass is. Grams cancel. You now have some number moles NaCl. You then take that number and put it over 0.100 liters of water to find your concentration of NaCl as prepared in units of molarity, moles per liter, okay? You now compare that, so you have some number here, and we have pi equals RT And this m here, remember, is our Van't Hoff factor times the concentration of the molarity as prepared. So this gets plugged in here. Temperature you plug in from the experimental conditions. This is the ideal gas constant, and you're given that information. And so then you simply solve for your unknown. So that is how you would do it. And the reason I didn't just make up numbers and go through it with the numbers is if I made up numbers, I could very easily have ended up with an I here that was going to be 68, which would make no sense at all. And I can't do that in my head to come up with what that number ought to be to start with. I would have to actually go through the calculation. Any clarifying questions on how this kind of approach works? Yes? I'm sorry? Use I in every single equation, yes. So the I is a modifier to the concentration. Okay, so the concentrations in these expressions, you have to remember, is the concentration of particles, not the concentration of formula units. And so you use an I to account for that. Now, if you are dealing with a non-electrolyte, you know what I is. I is equal to 1. So if you have a sugar molecule, a glucose molecule, so C6H12O6, well, this is a nonmetal, this is a nonmetal, this is a nonmetal. So just by looking at this chemical formula, you know this is a molecular compound, okay? You know that this is a covalent compound. And so when it dissolves in water, it stays as molecules of C6H12O6. It doesn't divide up into ions. And so your I is going to be 1 in that case. You really only need to deal with the value of I when you are dealing with an electrolyte, meaning a compound that creates ions when it dissolves in solution. Okay. All right. Would a 2 molar concentration of sodium chloride be expected to have a similar Van't Hoff factor to 1 molar magnesium oxide? That's an interesting question. So that's getting back to this comparison I made here, saying we got twice the charge here, so the attractions are going to be stronger than this. I don't know. Well, it wouldn't be twice, but the difference from the ideal might be twice. So if the ideal is 3 and this one becomes 2.8, then maybe this one would become 2.6. That would be a reasonable estimate to start with, I think, but I've never actually looked at data on that. So I don't know if I'm overlooking something with that. So as a result, I would not ask you something about that. All right, what else can we talk about? No other questions? I am happy to let you guys go early if you would like to. We have about 10 more minutes left in the time that we're here for. So, you know, if there are any topics that seem to be of particular confusion, even if you don't know what specifically to ask, I'm happy to try to riff on it. Okay, so the chat asks, is Henry's Law going to be on the exam? No, I'm not going to ask anything about Henry's Law. Was that in the textbook or was it in Newton? Anybody know? In Newton? The grading Excel sheet, yes, will come out after the exam. I don't know how quickly after the exam, but yes, it will be coming out after the exam. Henry's Law was in the content videos. I know Raoult's Law was in there, but I don't remember Henry's Law being in there. It's in the solubility video. Okay, I'll have to go back and look at that. So I don't remember bringing Henry's Law up there. So I'll have to remind myself of what I did. So no, I'm not going to be asking you questions about Henry's Law, no. All right, let's call it good for today, I guess. No sense in sitting here staring at our hands. Thank you, everybody.